let us look at another method of mix design today, the British DOE method. So, we shall generally discuss about the method itself, and since this method provides us with a methodology for designing concrete mix with fly ash or any kind of pulverized fuel ash, we will discuss that part also. Right. Now, this method, if you look at it, it starts in the same manner as the IS method or many other similar method. So, what we do? We first find out the target mean strength, we find out the target mean strength, that is TMS, TMS, target mean strength, and in the same manner as characteristic strength plus 1.65 standard deviation. So, we find out in the same manner as we have done for Indian standard method, and then the step 1, 2, 3 etcetera follows. So, let us just talk about the steps. Same thing, the basic philosophy of the mix design remains same in this method as well, like many other methods. We select the water cement ratio from a set of curves, then followed by that we estimate the water content based on slump, VB time, MSA and shape of aggregate. We determine the water content based on slump as well as VB time. Now, look at the difference. The Indian standard method had compaction factor here, this uses slump and VB time, MSA and shape of aggregate, right. Now, this is a direct from the single table. In Indian standard method, what did we do? We first obtain this from the curve, which is as a function of cement strength, the water cement ratio versus strength of concrete, composite strength of concrete is assumed to be a function of cement strength as well. Okay, this is similar, although here we do not do it that way. But the second step, we found out the water content and sand content first for a specific condition of workability, that is compaction factor 0.8, specific water cement ratio, and then specific grade of zone of sand, grading of sand, and then we applied some sort of correction factor. Here it is not like this, directly we find it out from a single table based on shape of aggregate and maximum size of aggregate and required slump etcetera, etcetera. So, in that sense that this is a one step method rather than a two step method. Then we find out the cement content, because we know the water cement ratio by this time. Through step 1, step 2 we have come to know about the water cement ratio and then the water content, hence cement content is known to us. So, with cement content known, next step remains to find out cement content is known, water content is known. So, then I can find out the total aggregate content, provided I have some way to determine total wet density as we call it. So, instead of calculating it out in terms of the volume of the solid and water, right, where you know the volume of the cement, volume of the water, rest of the volume will be occupied by the aggregate. In this case, it gives you a curve for wet densities of concrete, right, and then that wet density, from wet density we can find out the total aggregate content. And then in the last step we determine the fine aggregate content based on maximum size of aggregate, water cement ratio and grading zone of sand, or size, particle size distribution of the sand from at a set of curves. So, this is basically the outline of this method. We will just go one by one, each step we will look into again in details. Apparently, this is a very logical way of choosing water cement ratio, because you see it does not assume it to be a function of cement strength or something of that kind or specific thing. It actually uses water cement ratio as a function of strength is a function of water cement ratio when all other things remain constant. Only thing is starting point might be difficult. Well, with little bit of modification it becomes very logical, as we shall discuss. Then shape of the aggregates is also taken into account in direct one table. Of course, shape of the aggregate is also taken into account in Indian Standard Code method, because we said for rounded aggregate we reduce down the water content by 15 kg per meter cube and we reduce down the sand content by 7%. And then here there is a mixed design procedure with fly ash is also available, and precisely that is why the reason this seems to be a quite a logical method and seems to, and it is easily applicable to Indian situation also, because it deals with the cube strength, and Indian method is almost similar to this, there is some similarity. So, it deals with the cube strength, calculates out the target mean strength in the same manner, and therefore, that is why I have chosen, and more importantly it has got a, it has it makes us, it gives us a methodology for designing a mix with fly ash, this FS stands for fly ash, which was not available with other Indian method at the moment. I mean the code might change, but at the moment fly ash based mix design is available with this method, and that is the reason why this has been chosen as a second example. There are several other methods, but this can be easily adaptable to Indian condition as well. Okay. Now, let us see how this method go about. So, we said the first step is determining water cement ratio, right, water to cement ratio. So, Fm being known, I know my target mean strength. Now, I want to determine the water cement ratio, and these are the set of curves in x axis of this curve. In the x axis of this curve, I have got water to free water cement ratio, free W by C, and this side I have got compressive strength, F, Fm maybe I may call it, because I will use target mean strength on this side. So, this is what the set of curves are there. Now, each curve corresponds to a particular concrete, that means aggregate cement all put together. So, when each curve represents to a particular concrete, right, not just alone cement, but particular concrete, because strength of concrete is a function of water cement ratio when all other things remaining constant. It is the main function of water cement ratio, but other factors do affect, that is what we have seen, right. So, when all other things constant, for each case all other things constant, for this case all other things a second constant and maybe constant, and so on and so forth. So, this corresponds to a particular ingredients, set of ingredients, aggregate cement, everything, etc., and strength would vary like this. So, there are several curves, there are several sort of curves, and it tells us a method by which you can obtain, by which you can the starting point could be the strength here, starting point could be strength here. Okay. First of all, let us see what is the guideline of the code itself, and then now code, since it gives us a guideline that if you have OPC or sulphate resisting cement or any other cement, for several cements is given, this table is given, it gives you a table, and corresponding to this table for crushed and uncrushed aggregate, it gives you the strength, 28 days strength. This one I have chosen is 28 days strength, actually 28 days compressive strength. The table gives you 1 day, 7 days, 3 days, 7 days, etc. Several other strengths are also given, and for various types of cement, a part of the table is picked up here. So, this could be the starting point, and this is the 28 days compressive strength for water cement ratio, 0.5 for this line, for this line, this is for strength for W by C equals to 0.5, this is W by C equals to 0.5, that is a guideline they have given. Now, this guideline may not be suitable for our condition. So, therefore, this exactly cannot be adopted in our situations, because this strength may not be available for our all OPCs in India with all kind of crushed aggregate is unlikely to give 40. The best way is to do a trial mix, and in the trial mix what you do? You cast any workable mix with water cement ratio 0.5, cast any workable mix. So, cast any workable mix, the step would be cast any workable mix, cast any workable mix, right, cast any workable mix, any workable, cast any workable mix, any workable mix, any workable mix, it should be flowable, just you should be able to compact mix with water to cement ratio is equal to 0.5. Get the results, maybe 28 days results, well you have to wait, but that is okay if you are waiting. If you are first time, possibly you might take a longer period of time, but once some results are available with a set of aggregate and concrete, same thing can be repeatedly used very easily. So, that there the advantage of this sort of method comes in. Supposing when I want to do monitoring of concrete strength in quality control system. So, there is a little bit of change I want to find out, I can use these curves very easily, right. So, because it is not dependent on cement strength or anything of that kind. So, in case I want to find out in my situation, what I would do, I would actually cast any workable mix with water cement ratio 0.5, take that strength. For example, let us say my strength comes out to be something like 20, 25 or so, 24 or so. So, this is the strength that comes in 25. I find my strength is equals to 25. I find my strength is equals to 25. Now, then this gives me a way to select this curve. So, my curve is now the curve that I will be using for my purpose. Curve that I will be using for my purpose is this curve. So, curve selection can be done. One way is to take the tabular values, but that will give you only one curve. That is not that is not really the right thing, because this is meant for some, it has come from some results which have been done in UK and will not fit it to the Indian situation. To fit with the Indian situation, I must have some data, preferably not preferably, suggested that I should have one strength 28 day strength at 0.5 with my aggregate cement system, etc., etc. So, starting point could be that I start that way, and if I know the strength, for example, if 0.5 water cement ratio, my strength comes out to be 25, 20 and 30. So, this is 25, then I pick up, this is my curve, I pick up my curve as this curve. Then what I do, supposing my target mean strength is 32 as shown here, target mean strength is 32, target mean strength is let us say 32, then I go to 32, target mean strength is 32, this is my 32, and I draw a line here, come up to this curve and find out the corresponding water cement ratio. Let me repeat this process, let me just repeat this process again, let me repeat this process again. How do we find it out? First of all, what I do, I actually find it out what is my, which is a curve, and to do that what I do, I first cast any workable mix with water cement ratio 0.5, find out the strength and identify this curve. Now, I know my target mean strength. Since my target mean strength is known, what I can do, corresponding to the target mean strength, I find out what is my water cement ratio using this same curve. So, I use this curve to find out what is my water cement ratio. That means, if 32 was my, let us say, target mean strength, I draw a line like this and then drop it down to find out my water cement ratio is 0.43, water cement ratio is 0.43 as can be seen here. So, that is how we determine the water cement ratio. In this case, if you are in UK, perhaps you can use this, but in any other situation you cast any workable mix and choose the curve from the first test results. It will take time, yes, first time it will take time, but if one result is available, then next time it is not a problem. In fact, in monitoring these curves becomes very helpful, right. Okay. So, following this up is following this up with this is now these curves can be easily formed into set of equations. We know, if you remember, that we talked about Abraham's water cement ratio law, and which looks like this. Abraham's law looks like this, Abraham's law looks like this. It is F equals to A divided by B to the power water cement ratio. That is what it is. Abraham's law would look like this, F equals to A divided by B to the power W by C. And then if I write K2 as B to the power minus 1 and K1 as A, right, A and B to the power minus 1, then my strength can be written like this, F K1 K2 W to the power C. So, what we can do, we can actually express all these curves in form of a simple equation like this. So, all these curves can be expressed, they represent Abraham's law. Now, there are two constants k1 and k2, and by simple regression analysis one can determine this k1, because if you take logarithm of both sides, you will find that log f is equals to log k1 plus w by c log k2. The logarithmically, if we plot log f, it will be linearly related to water cement ratio. So, all these curves can be fitted into a set of equation like this. F1 is equal, f equals to k1 into k2 to the power w by c, where k1 is given like this and k2 is given like this. Now, this k1 is related to 0.5 f 0.5, that is the strength at 0.5 f 0.5, that is strength at 0.5 water cement ratio. So, this same thing, the exercise can be done for 7 day strength or for 28 day strength as desired, but the relationship would be like this. F 0.5 in case of 28 day strength will be the 28 day strength with 0.5 water cement ratio for your materials, and k1 is related to this in this manner, k2 is related to this, k2 is related to f 0.5 in this manner. This is why all this curve through a regression analysis can be given in this form of equation, k1 here, k2 here, and therefore, the strength you can find out. So, this can be easily worked out in Excel sheet also without going through the curves, because these days it is very easy to work on Excel sheets, and through this equation you can find out. Well, so this is how we can determine water cement ratio. This is how we can determine water cement ratio, first from the curves and then same equations can be there. Now, having done that, having found out that water cement ratio, the next test would be water content determination, and this is simply done from a table. The table, this table looks like this, is a part of the table again. This table will look like this. This is a column for MSA, 20 mm, 40 mm, there is one for 10 mm also. So, I have just not taken that, because that is not really part of the table, is required for our understanding. Then aggregate type is given, crushed or uncrushed, crushed or uncrushed, like uncrushed means natural gravel or natural land quarried sand maybe, or river sand. So, these are all uncrushed. Crushed means crushed aggregate, crushed sand or crushed quartz aggregate. So, when you have combined aggregate crushed, then for this slump 0 to 10 slump, the water is 170, for 10 to 30 190, 60 to 180, in between there are one more column which I have not put in. So, you see the water content can be determined from a table like this, knowing the maximum size of aggregate, type of aggregate, that is crushed or uncrushed, because the shape of the aggregate has been classified into two classes, crushed and uncrushed. This is the shape of the aggregate, because this is rounded, this is angular. So, shape of the aggregate has been taken into account here, and you can see when it is uncrushed it is much less and the water required is much higher when it is crushed. That we understand, because packing quality is better. So, it will require less paste, and therefore, for a given water cement ratio will require less water. So, this is clearly understandable, and as I increase my slump I require more water, as I increase my slump I require more water, and as my aggregate size increases this will also reduce, because my packing becomes better. So, as the aggregate size increases this quantity reduces, because the packing becomes better, I have a better pack system now. So, therefore, you can see that the water content can be determined from this table. Very easily one can determine the water content from this table, knowing the MSA, knowing the slump, and corresponding BB times are also given, although I have not included in the table. Range of BB time, for example, how much second, this is milliseconds or seconds, these are given, and according to 0 to 6 and 6 to 12 etc., seconds, these are also given. So, water content can be simply determined from this table. Okay. Water content being known, cement content being known, say water cement ratio being known, I can calculate the cement content. I know water content, I know the water cement ratio. You see, water content is known, water cement ratio is known, I can calculate out the cement content, and cement content is calculated like this, like before, like as in the case of Indian standard method. Water cement ratio star, that means the what that one you will be using is the minimum of water cement ratio you have determined from the curve, and water cement ratio that you have determined from durability requirement, same table. The table that we have used earlier is the same table, and this is determined from the curve. How I determine from the curve? First I make a trial mix to find out, choose a curve, and how from the trial mix I find out 28 day strength and put that onto that curve as we have discussed. And when we choose a curve, choosing a curve, the next step is to find out my water cement ratio required for my target mean strength, and that is what we do, and then compare this with the durability requirement, whichever is lower I take that. Then one additional thing, water content I have determined for crushed or uncrushed aggregate. Now, supposing I have got mixed aggregate, say sand is natural sand whereas coarse aggregate is crushed, right, or for that matter I have say natural gravel and crushed sand. So, both ways it is possible. Then the water content is taken by it is obtained by this formula, where this stands for W is the water content, which is 2/3 of the water content for the fines and water content from the coarse aggregate. In other words, supposing I have got a fine I have got the fine as a natural fine say land quarried or river sand, whereas the coarse aggregate is crushed. So, water content required for the crushed aggregate will be taken divided by 3 plus water content, let us say this value was for the crushed, let us say it was 170, let us say WC was 170 crushed, and corresponding for the for the natural fine aggregate WF was 135. Then my water content will be given as sum total water content will be given as it will be given as 170 divided by 3 plus 135 into 2 by 3. So, one can find out the water content in this manner when you have got mixed aggregate. For single shaped aggregate, that is not the problem, for multiple shape you find out in this manner. So, use this water content now together with the water cement ratio that you have determined to find out cement content, which will be W divided by W by C star, W divided by W by C star, and C durability, whichever is higher. In other words, let us just look at this again. Let us look at this again. W divided by W by C would give me cement content, right. So, this star is known to me. So, I find out the cement content in this manner. Compare this C with C durability, whichever gives me the higher value I choose that cement content. So, by doing this, therefore, we have found out the cement content and we have found out the water content. The next step is to find out the total aggregate content, and this is done using what is called wet density method. So, instead of calculating volume calculation, total volume minus the volume of air, this uses a method for wet density, which has been empirically established, and you can see the wet density curve. This looks like this. The wet density curve has got on the x axis it has got free water content, and the y axis it has got wet density of the concrete, and there are different specific gravities of the aggregates given here. So, or the combined aggregate actually. Now, supposing I have got less specific gravity, obviously the wet density will be lesser. Higher the specific gravity of the aggregate, wet density is higher. And again, as the water content, because you see the aggregate has got a specific gravity of 2.6 or 2.7 or up to 2.9 from 2.4. Cement has got a specific gravity of 3.15, whereas water is the material which has got the least specific gravity or least density. So, its contribution towards the wet density will be least. So, as the water content increases, the wet density reduces, and it has been plotted against for various specific gravities, because cement specific gravity is by and large same. Then how do I determine? Supposing my water content is 180, and my specific gravity is around 2.65 combined aggregate, then my wet density will be somewhere here, 2400 and maybe 50 or maybe 10 or something like that, whatever it is. So, I can interpolate in between and find out. So, wet density therefore, I determine in this manner, total wet density I determine in this manner, that is when I know the free water content, knowing the specific gravity of the combined aggregate, I can determine the wet density. And once I have done that, what I do next, I calculate the total aggregate content using this formula. Total aggregate content is the I express it in this manner. Total aggregate content is equals to wet density d wet, let me call it, minus cement content minus water content, minus cement content minus water content. So, because wet density will be the sum total of material, mass of the material. So, this is in basis of mass straight away, no volumetric basis, and error due to assumption of air content and all this is actually reduced. So, mass of the cement I know, mass of the water I know, and this would be water in 1 meter cube I know, and if I know the wet density, which is the total mass in 1 meter cube. So, in 1 meter cube cement and water I just subtract, rest all must be the aggregate, rest all must be the aggregate, because mass will correspond to the aggregate only. So, mass will correspond to the aggregate only. Then the next step would be determination of fine aggregates based on maximum size of aggregate, maximum size of aggregate and water cement ratio, grading zone of sand from curves. So, that is what next step, because so far I have found out total aggregate content, I have found out the total aggregate content. Now, if I know the proportion of the fines in the total aggregate, then I have found out the coarse aggregate and fine aggregate, and that would do my job, that would do my job. Okay, let us see how do we do it. This is done from a set of curves. This curve looks like this, set of curves. You see, this curve would look like this. First of all, it will look something like this. In this axis, I have got proportions of fine aggregate, and remember this is on mass basis, not volumetric basis, unlike the Indian standard method, which at volumetric basis. There I found out the quantity of fine aggregate. I mean, first I found out the volumetric proportion of the fine aggregate in the total aggregate. This has been plotted as a mass basis total aggregate content, right, required, because I have fixed my cement content, I have fixed my water content, and therefore, I have fixed my total. The moment I have fixed cement and water content, in fact, my paste content is now fixed, total amount of paste in 1 meter cube was fixed. So, rest of the volume is filled in by aggregate, and the paste volume should be sufficient enough to fill in the voids in the coarse and fine aggregate system. So, if I use too much of fines, maybe the voids would be too large, not to will not be, the paste will not be able to fill it. So, therefore, appropriate fine content is required, and that is obtained from this sort of curve. So, on this side you have got proportions of fine aggregate, and on this side you can see the free water cement ratio, on this side free water cement ratio, and here is the slump. This is for slump 0 to 10 millimeter, 10 to 30 millimeter, 10 to 30 millimeter, 30 to 60 millimeter, and 10 60 to 180. Corresponding BB times are also given, 0 12 second, 6 to 12 second, 3 to 6 and 0 to 3 seconds, etc., etc. This increases, this of course will decrease, as we have understood earlier. So, and this is for MSA 10 mm. Similar other curves are available, as we shall see later on, for MSA 20 and MSA 40, we shall see that. Now, here look at these curves. If you look at these curves, there are no lines actually. As the water cement ratio increases, as the water cement ratio increases, in fact, my fine also increases, because now water cement ratio increase means for a given cement, given cement content and water content fixed, higher water cement ratio means actually higher paste volume, and this paste volume must be occupied by larger volumes of fines, and that is why there is an increase as I go along this direction. And these curves, each of them represents actually kind of size or grading zone or fineness of the sand. Earlier of course, they are given in these zones, these are given in terms of zone 1, 2, 3, 4, and this would corresponds to zone 1 of the sand, zone 2 of the sand, zone 3 of the sand, and zone 4 of the sand. Now, zone 1 sand means which is a coarser sand compared to zone 4, which is a very fine sand, relatively finer sand. Now, there is another way of looking at it, that line 1, the top line corresponds to passing through, percentage passing through 600 micron sieve is 15, which means only 15% passes through 600 micron. So, it is a coarse sand. This line actually represents a very coarse sand. Next one, 40% passes through the second line, second line. So, next one, this line, for example, this line corresponds to 40% sand passing through 600 micron, 40% sand passing through 600 microns. That means 60% is still bigger size. In this case 85% was bigger size. So, this is a finer sand. This one 60% passes through, 60% passes through, this line corresponds to 60% passing through 600 micron. So, most of the, and here this one corresponds to all being finer than 600 micron, all being finer than 600 micron, right. So, as you have finer sands, coarser sand, you require more quantity of sand in the coarse aggregate system. In the finer sand, you require less quantity of fine aggregate in the system, and in total aggregate, in the total aggregate. So, that means if you have something like a slump of, let us say, dealing with slump of 70 or 75, somewhere in between this, or 100 millimeter, then, and you have got this fine sand, for sand, let us say I have got the finest of the sand, everything passing to 600 micron, and my water cement ratio is somewhere around 0.45, something like this, 0.45, let us say, then my percentage of the sand in the total aggregate will be around 33%. So, I will have 33% of the sand in the total aggregate system if my MSA is 10 millimeter, So, this is how I determine the sand content, right. This is how I determine the sand content in total aggregate system. Same curve, similar curve is there for 20 millimeter aggregate. There is another curve, set of curve for 20 millimeter aggregate, and you see this same thing, proportions of fine aggregate. And similarly here, let us say if it was a 20 millimeter aggregate, let us say this was my water cement ratio was 0.5, my water cement ratio was 0.5, and let me see, say this was 0.5, and I have my slump around 100 I needed, and everything was passing through 600 micron is this. I will need much lesser sand now, because my maximum size of aggregate has increased. So, this curves is now coming down, because MSA has increased, the void in the coarse aggregate system is lower. So, I will require lesser, lesser fines, I will require lesser, fines, right. Now, if I use less fines and less coarse aggregate, it will automatically mean my paste is of course, paste is higher, but at the moment I have already fixed my paste content. What I am trying to do is, my paste content is fixed, I am trying to determine the ratio of coarse to fine aggregate. So, in this case this would have been something like 28, earlier case you have seen it was about 32. Since my MSA has increased, this has reduced down by about 3-4%, right, for the same sand. If the sand was a coarse sand and same water content, I would have got something like about 50-55% for this kind of slump. So, I needed much more fines, because you see it is aggregate, the mobility of the aggregate, I need more paste, more mortar even. So, the more mortar is ensured by this. So, in case of coarse aggregate, so more fines, and they would pack into the voids of the coarse aggregate system, larger size they are. So, they would have, even when I have this 15%, it means 85% is passing through this. That means this one is a better graded sand rather than this, because in this case everything is fine size. In this case there is a mixture of everything, there is 15% above 600 micron. I mean, somewhere here would be a better situation, 15-60% possibly above 600 micron, but others are somewhere, this is a coarser side. So, you have got larger size also there in this particular one. So, this curve, using this curve, then we can determine the fine aggregate content. Similar curve is available for 40 mm aggregate as well. This is the curve for 40 mm aggregate. This is a curve for 40 mm aggregate. So, for different sizes of the aggregate, different MSA and different slumps, different workability, that is, and for various water cement ratios, once I know my cement and water and total aggregate content is known, the proportion of the fines in the total aggregate content, total aggregate system is now determined from these curves, and you can distinguish this from what we did in case of Indian standard. In Indian standard, all these were actually calculated first for a specific water cement ratio depending upon your grade of concrete, and for specific compaction factor, specific zone of sand, and the grade of zone of sand and shape of the aggregate, etc. And then we applied correction factors for each of them. Here, of course, fine aggregate content you determine here straight away from this sort of curves. But another difference is, here I am finding it out in mass basis, that is, the proportion of fine aggregate is with respect to total aggregate, both are in mass basis. Earlier in case of Indian standard it is in volumetric basis. So, doing this, after doing this, then I know now what is my fine aggregate percentage. So, now I can calculate out the fine aggregate content, and the fine aggregate content is simply this p value that you have got 28 or 32 or whatever we are just looking right now. Whatever I get Pw on the mass basis, I am calling it Pw because it is on mass basis, multiplied by the total aggregate, that is the W aggregate, it is the total aggregate content. This is what I have found out from the curve, this is what I have found out from this, this to find out this, I found out this one from the graphs, that is the straight line plots that which you had, graphs that I have just shown you. W aggregate was obtained from wet density minus the cement content minus water content, and now I find out the fine aggregate content. So, fine aggregate content is simply this multiplied by total aggregate, which I found out as d wet minus W aggregate, if you remember, just for the recollection, d wet minus W minus C. So, this being known, W aggregate being known, multiplied by Pw obtained from graph, obtained from graph, obtained from graph, and I just have the fine aggregate value. I have just have the fine aggregate value. So, this is how I determine the fine aggregate. Having determined the fine aggregate, I can find out the coarse aggregate, simply W aggregate, total aggregate minus the fine aggregate. So, then I have determined water, cement, coarse aggregate and fine aggregate, all these things are now known to me. So, this is the procedure meant for DOE method, but we will look into the fly ash, how we take care of the fly ash, but let us just discuss a little bit. So, what we have seen in this process, the stepwise, first step of course the target mean strength, then followed water cement ratio from curves which are not, which are actually is true, I mean a better representation of the Abraham's law, strength remaining, strength as a function of water cement ratio, all other things remaining constant, and they can be fitted easily to equations also, taking f 0.5, that is the strength at 0.5 water cement ratio as a parameter, input parameter, you can just determine in form of equations as well. So, input parameter in this curve is again f 0.5, f 0.5, that is the strength at 0.5. So, you can cast any workable mix which will actually, any workable mix which will with 0.5 water cement ratio, find out the strength to pick up the curve. So, you plot this value with 0.5 water cement ratio and the strength, you will get 1 point. This point will lie on a line, one of those curves, one of those curvilinear lines, and that curvilinear line represents your concrete. So, once you know that your concrete, correspondingly what is the water cement ratio for the target mean strength you can find out. For all set of mixed design, supposing you are doing M25, M30, M40 with the same aggregate, set of aggregates, well you need only one preliminary test to choose your curve, after that it is all same. Secondly, if you are monitoring, because it is not, the mixed design is not the end, it is the starting point, it is the starting point. You see, mixed design doing at some laboratory does not serve much of the purpose, it has to be done at the site, and you do it at the site, find out the mixed proportion, and then once you are actually obtaining the concrete, you continuously test those concrete cubes as a measure of the quality control. So, when you measure them as a means of quality control, you can now find out whether actually whatever strength you are providing or you are expecting, are you getting it or not. Now, supposing you are not getting, which quite often would happen, either you are getting it lower or you might be getting it higher, let us say. If you are getting it higher, then actually you are wasting your cement, you can reduce your cement. If you are getting it lower, you are not giving, you are not providing, you are not supplying, or you are not generating, producing what you are supposed to produce. In such case, again this curve will come handy, because it is for your set of material, the curve has been already identified, you can just pick in, you can just you can just shift, reduce the water cement ratio a little bit using this set of curves. The equation is there, from that also one can calculate out. So, that is the advantage of these curves, quite easily adaptable in monitoring the strength also, monitoring the cube strength also in quality control, it is much easier to use these curves. Okay. Now, that is the first step. Then second step is to determine the water content, and which is based straight away on workability, maximum size of aggregate, and the workability you require, both given in terms of slump and BB time, and slump is is more popular, used in site, and therefore, it is a more useful way. rather than doing BB is not very common, neither compaction factor is. So, that is another advantage, that it is also related to slump and you do not have to do a recalculation, and then you can straight away obtain the water content for various slump, various MSA and shape of the aggregate, and you do not need to calculate in more than one step, just get in from one table. Once you have got it, water content is known, water cement ratio is known, you can find out the cement content, and both cement content and water content known, your paste content is fixed, and if you know the paste content, if you know wet density of the concrete which is given in again in curve form, you can find out the total aggregate content. Then again the ratio of the fine aggregate is given in mass basis. So, that is again an advantage, there is no volumetric basis, not calculation based from any equation and things like that, simply you can find out. So, this method is quite simplified and appears to be more quite logical and very useful in monitoring monitoring the cubes, monitoring quality control and monitoring. Second point I would like to make is that mix design should be done at the site itself. It is such a simple method as we have seen, and it should be monitored time and again, otherwise there is no meaning, because you change one of the ingredients, the mix design may not remain same. Maybe there is some some maintenance of the mixer machine or the batching plant has not been done properly, mix design will not remain same. So, getting a mix design done once and not that too in somewhere in the laboratory and not in the site, and then using it in again and again has got not much of a meaning. It has to be continuously monitored and accordingly it has to be changed. So, in the quality control system there has to be a way to rectify or take kind of retrospective action on the concrete mix to correct any problem that has taken place. So, monitoring is very important in the quality control system, and this sort of curves are very helpful in this sense. So, mix design has to be done that way. It is not a very difficult job, it is simple, but its emphasis is again that it has to be done at site and time and again it has to be monitored. Now, I think we can look into the fly ash application of fly ash in the concrete mix design. Now, first thing to do that also I must have control mix made. That means, first without fly ash I have a control mix, right, and first I find out the control mix, that is a mix without fly ash. Then I got to take a decision, either it should be specified by the client, owner or anybody, or it is can be my own decision to use a particular percentage of fly ash. PFA is nothing but pulverized fuel ash, fly ash is pulverized fuel ash, and that is what it is. So, I must determine the PF, that is percentage of fly ash that I am going to use, that should be determined, and it should be known. Determine means it should be known either from specification or I make my own decision. Quite often, like if it is not a special concrete like high volume fly ash concrete, normal concrete, one can use whatever is permitted by the code or whatever percentage I can use and take benefit of, right, because as much as I use in the concrete, that is beneficial both from environmental point of view and also from economic point of view. So, but that decision how much I got to use, that first must be made, and that PFA percentage of PFA must be known to me. Then we have, if you remember, fly ash acts almost like somewhat like plasticizer, similar effect because of its spherical shape. If you can recall the discussion we had, the effect of various kind of admixture on workability of concrete, we said that for the same workability, same cohesiveness, fly ash would reduce down the water demand because of its spherical shapes, and generally the sizes being fine, they will have some sort of pore filling effect, and also they can have ball bearing action, and therefore, they reduce down the water content. So, first thing it does it reduces down the water content. So, I must have a way to find out how much is the water content, right, and let me say my new water content is W dash and original control mix water content was W, then W dash will be W minus delta W. This is first I did a control mix, as I said I do a control mix, right. So, that is called control mix, fly ash is used in the mix control mix. So, first I find out the control mix, calculate for the control mix, and from the control mix I find out how much the water I can reduce depending upon this, and this method provides us a way to do that, some sort of guideline. This fly ash must be sufficiently good quality satisfying the relevant standard 3812 IS 3812 in our case. By and large the specifications are more or less similar to the specifications elsewhere. So, this sort of table might still be applicable even in our case. That means, this table says how much is the reduction in delta W, how much is the water content, reduction in water content is possible. This table talks of delta W, this table talks of delta W, this table talks of delta W, right, this table talks of delta W. So, this is the water content reduction, right, this table talks of delta W, the water content reduction. Okay. As you can see, as my fly ash content increases, this is the fly ash percentage in cement. So, as my fly ash content increases and depending upon the slump, I can reduce, this is the quantity of water that I can reduce. For example, 5 is the delta W here, 5 is the delta W here and 10 is the delta W here. So, this is 10, 10, 15, 20, 20, 25. So, depending upon the amount of fly ash I am adding, percentage in the cementitious material, this is the amount of water reduction that is available. This is given in a form of a table. Therefore, if I know how much is the PF that I mentioned earlier, I can find out how much would be my reduction in water content, right. Okay. Now, this should be PF, actually this should be PF, this should be PF. Right. Now, you can see that this PF is F divided by C dash plus F, where F stands for the fly ash. So, P stands for fly ash percentage in total cementitious, where C dash is the cement content, F is the fly ash content. So, F divided by C dash plus F, that is the percentage of fly ash. P represents the percentage of fly ash in total cementitious, percentage of fly ash in total cementitious. And therefore, from this expression just rewriting, rearranging, I can get an expression for F. F will be given as P multiplied by C dash divided by 100 minus P, 100 minus P. Okay. So, now I have water to cement star, which was earlier there. The equivalent thing here given when I am using fly ash is water W dash divided by C dash plus Kf. You see, all fly ash, for example, if I add F quantity of fly ash, all fly ash do not contribute towards the equivalent water cement ratio. I can now define a term called equivalent water cement ratio. Now, equivalent water cement ratio is W dash, that is the water that you are adding, divided by C dash, that is the cement you have, plus F multiplied by K, Kf. So, this K is less than 1. If K was equals to 1, that means all fly ash also behaves like cement, but K being less than 1 tells us that I have possibly some fraction, some part of the equivalent cement. The total, if F is the total fly ash present in the cementitious, then F into 0.3, K is taken as 0.3 is a guideline. One can have its own K, decide his own K from their own test, but K is 0.3 can be a conservative value. One can start with this, but then determine his own K and find out as it changes. So, C dash plus Kf one can take it, right, and this is the then equivalent cement content, and W dash is the water, there is a water that I have obtained, water content I have obtained after reduction. So, my equivalent water cement ratio in case of fly ash concrete will be given by this, and this must be equals to the water cement ratio star of the control mix. So, my control mix had water cement ratio star, and this must be equals to W dash divided by C dash, where C dash is the cement in the new mix, fly ash mix, multiplied by K plus F. By just simply rearranging I can find out C dash, which will be given as 100 minus P, because I will put F from this expression. If I put F from this expression here, that is P C dash 100 minus P, then P is known to me, because P is the percentage of the fly ash in overall cementitious, and that is the first thing I have decided. Right in the beginning I have decided what is the P, because I said that you want to use 30% fly ash in the cementitious, well fine, that is what you take, 25% and so on and so forth, and that decision either has to be specified or one has to make that decision in the beginning. So, P is known to us, P is known to us, P is known to us. W dash we have found out, because W dash is nothing but original control mix W minus delta W dash, which we have found out from the table. So, 100 minus P into W dash divided by 100 minus 0.7 P and also divided by W by C star, which is known to us. So, this will give us, rearranging this, I get an expression, and putting F equals to this value, I get an expression for C dash, and I have taken K equals to 3 in this expression, therefore, it comes out to 0.7. So, cement content therefore, in the overall mix I have found out, and now knowing the cement content I can find out F, because C dash is known, P is known, C dash is known, P is known, F is known, therefore. So, F is known, I can find out, P being known, C dash being known, I can find out F. So, F is known, W dash is known, and C dash is known. 3 things are known to me. But then one more thing, I must compare this W by C dash in any case, W by C dash, of course, with the durability requirement, whether I am satisfying the maximum, but there is an advantage. While comparing the durability, I need not compare W by C dash. In fact, I can compare W by C plus F. So, maximum this I can compare, and similarly for minimum cement content I can C plus F I can compare. So, take total cementitious while taking consideration of the durability, and take water by total water cementitious ratio instead of cement. Cementitious means cement plus pozzolana, cement plus pozzolana. We have mentioned this earlier also in connection with the in connection with the types of cement and workability and strength, etc., and the role of this supplementary cementitious material. We looked into the microstructure with supplementary cementitious material, you remember, and we said this supplementary cementitious material actually improves the microstructures and reduces the permeability, therefore gives us better durability. So, when it gives us better durability, therefore, I can take whole of the cementitious material into consideration. Well, so while calculating the water cement ratio, maximum water cement ratio, instead I can take water cementitious ratio. Similarly, I can take minimum cement content, I can take C plus F complete, but there is one restriction as per our code. Currently, it says that the F value which you can take should be as per whatever is permissible in relevant code for Portland pozzolana cement. Portland pozzolana cement allows now 25% as P, 25% as P, which would mean that 25% is of the total cementitious is your pozzolana, right, which means that you are using roughly about one third cement, and its 1/3 is added to as pozzolanic material, fly ash. So, that is of course, this may get modified, this is likely to be modified, one might possibly use higher, but at the moment at 1489 IS 1489 part 1 allows P equals to 0.25 25, and therefore, F that you can take should corresponds to P 0.25 only in this calculation. That is what is the stipulations or recommendation of Indian Standard Code. So, while durability you can use, so therefore, at the moment there is not much benefit using P by P more than 25, because in the durability calculation this will not give you an advantage, although it might give you other advantages, heat of hydration, many other advantages, but durability calculation it is not going to give you more advantage, because it is restricted by the maximum percentage allowable in Portland pozzolana cement code, that is IS 1489 part 1. So, while calculating the water cement ratio, maximum water cement ratio, you can take W plus C plus F, but the F should corresponds to P equals to 0.25 if P is more than 25. If P is less than 25, take that value straight away and find out F as you have obtained here. Similarly, calculating total minimum cement content C plus F, use that F which is determined from this if P is less than 25. If P is 25 or more, if P is more, then use P equals to 25 here to calculate out the F, and that F can be used for minimum cement required. Maximum water cement ratio, same thing can be done. So, that is how I can take care of the durability aspect. That is how I can take care of the durability aspect. Well, wet density is assumed to be same as that of the control mix, and therefore, total aggregate content you calculate out in the same manner d wet minus C dash minus W dash minus F. So, you have got the wet density and fine aggregate is calculated again in the same manner as before. So, we calculate the fine aggregate in the same manner as before and total aggregate content we calculate in the same manner as before and wet density from the same curves. So, therefore, I have been able to now find out all the proportions. In this case, that is I have been able to find out the cement content, been able to find out the water content which will be lower than the control mix, cement content obviously will be lower than the control mix, much lower, and then I have been also able to find out the fly ash content corresponding to my requirement, and then of course, I have been able to find out the fine aggregate content and coarse aggregate content. One important point here is, you see, although we said that the water reduction takes place when we add fly ash, slumps do not reduce immediately, or rather it may not show you slump reduction. In fact, what it shows is with a lesser water content when you add fly ash you will get same cohesive mix. So, for your all practical purpose of placing, compacting, you will have same effort required, right, but slump itself may not exhibit the same thing. In other words, when you have fly ash concrete, even if you have a lower slump say by 25 millimeter, still you can consider it to be as good as the same in terms of workability, it is as good as a concrete without fly ash having 25 millimeter higher slump. So, let us say 100 millimeter is a slump of the concrete without fly ash. Now, I have reduced the water and done the mix design like I have just mentioned. The workability now I get in terms of slump, let us say is 75, still they will have similar, like even the slump is 75, still they are acceptable, because 25 millimeter reduction in slump is allowable, they give similar cohesiveness. So, that is what we do in case of fly ash mix design. So, I think with this we conclude our discussion on mix design of concrete and in general discussion on concrete, right. So, we have looked from production of concrete to effect of various materials and finally we looked into the mix design procedure. Today we have discussed, first we have discussed IS method last class, then we have discussed now the DOE method, another method, and lastly mix design with pulverized fuel has also been discussed. So, thank you for hearing.